Hello students, thank you for visiting our Easy BTech YouTube channel, and we are here to provide you all the courses across all the streams of engineering. All these courses are taken by experienced faculty and eminent faculty, and these courses will be delivered in a very simple and elegant manner so that you can easily understand the concepts and excel in your final exams. Apart from these engineering courses, we also provide training for your placement exams also. So I strongly recommend you to subscribe and subscribe this channel and hit the bell icon so that you get regular notifications in your mail. Welcome to this fascinating course of signals and systems, and I am Sri Hari and I will be your instructor for this course. I have split the first lecture in this fashion. First, we will try to understand why we should study the concepts of signals and systems, and then we will see what are the topics that will be uncovered in this course, and finally we will see the brief introductory part. Okay, so the very first question that rises in our mind is why we should study signals and systems. So one line answer is that they are part of our daily life, and applications of concepts of signals and systems is extraordinary in the sense it is applied in multiple areas of research which are listed here, but they are not limited only to these areas. So the concepts of signals are applicable even in, for example, economic forecasting and so on. Or for example, if you take communication systems, what happens? So the received signal from a noisy channel would be noisy, and hence what is that we have to do some signal analysis on the received signal, and we have to design a system such that the output of that system is more reliable signal. And in aeronautics same is the case. So for example, a pilot who is sitting inside the cockpit, definitely whatever is communicating to the base station is noisy because of the external noise which is produced in the cockpit. So definitely at the base station we should have a system which will receive the signal and try to extract the reliable signal from that received noisy signal. And for example, if you take image processing, so definitely, for example, if you take the images sent by the satellites, so they are very noisy, and definitely what is that we have to do? We have to do what is called image enhancement. So the signals which are received from the satellites are noisy images, and the systems which are designed again at the base station, they are called image enhancement algorithms, and they will give us the more enhanced versions of the images. And apart from that, for example, if you take control system engineering, for example, you take a power plant. So definitely if you have we have a huge boiler inside the power plant, and we have to maintain a constant temperature inside the power plant so that the power is produced without any hindrance. So if there is any drop in temperature, or if there is any increase in temperature, the sensors are set around the boiler or inside the power plant, so they have to sense it, and accordingly they have to take the decision. So that is even in chemical processing plant also the same is the case. So for example, if you want to maintain the same temperature and so on, so we need sensors which will give us the signals, and from these signals we will try to extract the information, and from that we can try to control the plant. Okay, and apart from that, for example, in biomedical engineering, let us take a basic example of electrocardiograph. So again, what we do, we put sensors near the chest and we extract the signals, and from these signals we pass it through electrocardiogram, and we have a system inside that which will try to tell whether your heart is working properly or not. So based on that, the doctor makes a decision to go to angioplasty or not. So in this way, there are multiple areas where we can apply the concepts of signals and systems. So with this brief overview, Hopefully, I have made it clear why this is a very vital subject in our curriculum. Okay, right. So to understand the concepts, to understand how do we apply the concepts of signals and systems in these varieties of applications which we have seen. So first we have to understand the fundamental topics that are needed and necessary to apply the concepts of signals and systems in these applications which we have seen before. Okay, and to add to that, so what is that we are going to see? So we have split our course of signals and systems into mainly 8 chapters. In the first chapter we will have the thorough background of complete concepts, fundamental concepts which are needed, and it's a big chapter. Okay, so we'll see a lot of topics in the first chapter, and then we move on to the second important chapter, which is linear time invariant system. In this chapter we will try to understand a very important concept of convolution summation for discrete time case and convolution integral for a continuous time case. Apart from that, we will see many applications, and then in third chapter we move on to the understand the frequency content of a signal by using what is called continuous time Fourier series, which is applied for a periodic continuous time signal. And later we move on to an aperiodic signal, the frequency content of an aperiodic signal in the fourth chapter, which is called continuous time Fourier transform. Then we will expand the concepts of continuous time Fourier transform to cover the signals for which Fourier transform does not exist. So there we understand these concepts in the fifth chapter, which is Laplace transform. So then we move on to the discrete time domain, where in sixth chapter we'll talk about discrete time Fourier transform, and then we talk about the analogous version of Laplace transform for discrete time case, which is the Z transform, and then we will finally wind up this course with a very important topic, which is discrete Fourier transform. So this helps us in understanding how do we compute the Fourier transform of a signal, which gives us the frequency content of a signal on a computer. Okay, and how do we make these computation much faster by using what is called fast Fourier transform. Okay, then the textbooks which are used in this course are these are the two textbooks which we'll be using in this course. The first textbook is Signals and Systems by Alan Oppenheim, Wilsky and Hamid Nawab. Second edition is available in the market. And apart from that, we will extract few information from the second book, which is again Signals and Systems, but by Simon Hackin and Barry Van Veen. Okay, I think in market third edition is available. Okay, right. So let us conclude this lecture with a brief introduction, and in this we will so in the introductory before we go into the brief introduction, we will in the very first chapter what we study is this. So first we will try to understand the definition of a signal, and then we talk about the classification of signals, and then we talk about how the signals are plotted, and then we will see some very important signals like Dirac delta function, sinc function, exponential function, and so on, which are much useful in understanding the concepts of signals and systems. And finally we will talk about the systems and their properties like linearity, time invariance, causality, memory, and invertibility. Okay, so first and foremost thing in this course is first we should understand the definition of a signal. So what is a signal? A signal is a function which varies with respect to one or more independent variables, and that fellow should convey some information. Okay, so so concept of information is different, so that we will study in information theory. But what is a signal? So signal, it is a function that varies with respect to one or more independent variables, and that fellow should convey some information. and then we have to understand what is the dimension of a signal. So a signal, a signal depends on number of independent variables, and this number of independent variables we call it as the dimension of a signal. So for example, if you take a signal to be x of t, in x of t, t is independent variable and x is a dependent variable. Because x of t depends only on one independent variable, we say that the signal x of t is a one dimension signal. Okay, for example, x of t equal to cos t, sin t, t square, mod t, whatnot. So Gaussian function, sinc function, all these are examples of one dimension signal. And coming to a real-time examples, we have already seen like speech signal, ECG signal, all these are examples of one dimension signal. And similarly, if you want to have an example for two dimension signal, we can write it as f of x comma y. Why f of x comma y is a two dimension signal? Because it depends upon two independent variables x and y. Here x and y are independent variables and f is a dependent variable. So f of x comma y depends on two independent variables x and y, and hence we say that f of x comma y is a two dimension signal. So mathematically you can have infinite number of examples. Correct, you can have infinite number of examples. So one of the important real-time example is an image. Okay, so you can extend the dimension of a signal even to 3 dimension or 4 dimension or maybe n dimension, or if you go to extreme it can be an infinite dimension signal. Okay, for example, if you have f of x comma y comma z, then that signal is a 3 dimension signal. Similarly, if you have f of x comma y comma z comma w, that would be a 4 dimension signal, and in that way we can extend the dimension of a signal. So we can have a multi-dimension signal. So definitely if the number of dimensions starts increasing, the complexity of analyzing those signals also increases. Okay, so the last but not least is that in this course of signals and systems, we deal only with one dimension signal. So which we have seen earlier, and also we will be dealing only with a single valued signal. What do you mean by a single valued signal? At a given instant of time, a signal can take only one value. Okay, for example, as we have seen cos t, t square, mod t, all these signals are single valued signals. You pick up a time instant of time, it can take only one value. So we call those kind of signals as single valued signal. But why should we study single valued signal? Why? Because all our real time signals are single valued signal. So that motivates us to focus only on single valued signals. So question is, can we have multi-valued signals? Yeah, mathematicians, they are crazy, they can have any kind of signal, but for us the focus is only on single valued signal. So with that I will conclude this lecture, and we will see the more concepts in coming lectures. Thank you.